Last time we talked about basic exponential function where fx is base a to the x, and the a has to be positive and cannot be 1. I will explain later on why it cannot be negative, cannot be 0, and cannot be 1. Why a can't be negative, can't be 0, and cannot be 1. Okay, but maybe toward the end of the lecture today. Now, for example, the function for these basic exponential functions, like fx2 to the x, we even graphed it last time. Okay, 3 to the x, 2/3 to the x, and 1/2 to the x. So the base are these. Has to be positive and not 1. Now, all these exponential functions has domain all real numbers. The range is from 0 to infinity, not including 0, just positive real number. The y-intercept is 0, 1. Yeah, you can imagine if you plug in f0, that's a to the 0, that's equals to 1, right? Okay, x-intercept, there's no x-intercept. Horizontal asymptote is the x-axis, y equals to 0, and then when the base is greater than 1, the function will be increasing. If it is between 0 and 1, it will be decreasing. Let's take a look first, just to remind ourselves what we did last week. This is the graph for 2 to the x. This is a graph for 2 to the x. Now, as we have discussed earlier, that the y-intercept is 0, 1. Right? When you plug in x equals to 0, you get 0, 1, right? When x equals to 0, the y is 1. Now then, notice that when I move 1 unit to the right, I will multiply the previous value by the base 2. So when I move 1 unit to the right in x direction, then the y will be multiplied by 2, whatever the base is. If I move another 1 unit to the right, then the y will be multiplied by the base again, and so on and so forth. Okay, so every time you move 1 unit to the right, you double it, you double it, you double it, right? That's if you move to the right. Now, when you move to the left instead, so from 0 go to -1, then you will get 1/2, because what? You divide by 2. Divide by 2. Move another 1 unit to the left, you get 1/4. Divide by another 2. So on and so forth. Okay, so the further you go to the left, you keep on dividing by 2, dividing by 2, dividing by 2, dividing by 2, dividing by 2. Now, but because you start from a positive number, when you divide by 2, it's smaller, but still positive. That's why the range will never be including 0. Okay, the range will not include 0, because what? You keep on dividing a positive number by 2, it will still be positive. When I ask you to do graphing for the exponential function, I need you to provide me these 3 important coordinates. Okay, these coordinates are the one related to the y-axis. You move 1 unit to the right, 1 unit to the left. Now, when we do transformation later on, then these 3 coordinates in blue, these 3 coordinates that I highlight in blue, will also move. Okay, now the reason I want you to give me these 3 coordinates, because the graph actually bends the most actually in this region. The graph bends the most in this region, and the one here basically flat out, and the one here actually increasing super fast, but it's not bending as much as what we have here. That's why I want you to give me those 3 important coordinates. Okay. Now, suppose we graph, let's say 2/3 to the x. Let's say 2/3 to the x. 2/3 to the x, then the y-intercept is 0, 1. Move 1 unit to the right is 2/3. Another one to the right is 4/9, so on and so forth, right? So it is decreasing. Just imagine, because you multiply by a base less than 1, then it will get smaller, right? Okay, and then when you move to the left, you divide by 2/3. Dividing by 2/3 is the same to multiply by 3/2, multiply by the reciprocal. Okay, multiply by 3/2. So 3/2, 9/4, 27/8, right? So 3/2, when x equals to -1 is 3/2, -2 is 9/4, -3 is 27/8, x equals to -4, that will be 81/16. That's approximately 5. Like that. So the graph will be approximately like this. This is y equals to 2/3 to the x. Okay, now those three important coordinates I told you earlier are these things. This guy, which is 0, 1, 1, 2/3, -1, 3/2. Okay, now that's to review what we have seen last time from last Tuesday. Now, from these two graphs here, we see something very, very important. Something very, very important, that when the function, we know it actually from chapter, I think from chapter 3. When a function is increasing or decreasing, you can see then the function is 1-to-1. Why? Because whatever horizontal line you draw, it will hit the graph at most once. Okay, maybe not. Whatever horizontal line you draw, it will hit the graph at most once, or maybe not. Okay, so not only that it is a function because it satisfies vertical line test, it is also 1-to-1 because it satisfies horizontal line test. Now, because that it is 1-to-1, for that reason, then we can use this to solve. Then we see that 2 to blah equals to, maybe I instead of using 2, I use a. Base a to blah equals to a to blah implies blah equals blah. Okay, that's the consequence of 1-to-oneness. Okay. As long as the base are the same, then the exponent must be the same. Okay, so suppose a very simple example. So for example, 3 to the x equals to 3 to the 4. Then x equals to 4. Okay, but Thomas, I thought that's always true. Actually, no. Actually, that's not always true. If the function is not 1-to-1, the function is not 1-to-1, then it is not true. Now, for example, if I have x to the 4th equals to 3 to the 4th, does it imply x equals to 3? The answer is not only 3. Not only 3. In fact, x equals to 3, and x equals to -3. It is not one-to-one. Now, the graph of x to the fourth looks like this. It is not a one-to-one function. Okay, x to the fourth is not a one-to-one function, which means that even though this seems to be, oh, x must be 3, no, it turns out that x may be also -3. Now, but once you have a one-to-one function, then if they are the same, then it must be that one. An answer must be the answer because it's one-to-one. An answer must be the answer. If it is not one-to-one, okay, an answer may not be the only answer. Maybe something else. Okay, now using that property, then we can solve problems like the one we see between number 51 to number 57. Let's say, for example, I do number 52. Number 52, solve 2 to the x minus 3 equals to 16. Now, rewrite that 16 into a number with base 2. That's 2 to the 4th. Then by one-to-oneness, x minus 3 equals to 4, so x equals to 7. Is it okay? Now, of course, you may wonder, but Thomas, how do you know 16 is 2 to the 4th? Now, that one you need to figure out. Okay, it does take some maturity, but we do expect if you are in college algebra, you have that already. Okay, number 54. Solve 5 to the x minus 2 equals to 1 over 125. Now, 125 is 5 cubed, but because it is on the denominator, when I bring it up, it becomes positive, negative exponents, 5 to the -3. Now then, by one-to-oneness, x minus 2 equals to -3 means x is -1. Okay, now it may get more complicated than this, but not that much more complicated. Number 58, for example, e to the x squared plus 6 equals to e to the 5x. They already have the same base. Because they are equal, then the exponent must be equal. Then from there we solve as usual, just like solving a quadratic equation in this case. If you can factor, do so. If not, then completing the square or formula. Okay, that's for the solving equation based on the one-to-oneness. Now we will focus our effort this time for the next half an hour approximately to graphing. Basically, everything we know about a function that enable us to graph. Okay, let's start with the following example. For example, first big example, let fx equals to 2 to the x plus 3 minus, let's say, minus 4. Before I actually, we will need to answer the following question. We need to answer the following question. First one, what's the domain? And then what's the range? For us to answer these two, we need to know the transformation. The initial graph, the basic graph of 2 to the x, and what the transformation is doing. And in the third one, what happened to the y-intercept? I mean, what will the y-intercept be? And how about the x-intercept? It is true 2 to the x has no x-intercept, but after you move it a little bit here and there, you may have you may have x-intercept. Okay, so we know, for example, 2 to the x originally looks like this. Okay, it looks like that, right? But then you will move it 3 units to the left, and then 4 units down. So later on, your graph will look approximately like this. Okay, and the original horizontal asymptote that you have here, that's the original horizontal asymptote. When you move down 4 units, it will be y equals to -4. Okay, that's the rough sketch. So from here we see that we will have the y-intercept, of course, because the domain is all real number, right? But because you move it down, then the range will include 0. Okay, the domain is still all real numbers. Yeah, originally it's all real numbers. When you move left, right, up, down, then it will be still all real number. Now the range, however, originally from 0 to infinity, right? From 0 to infinity. Now, because you move it down 4 units, then the range will be from -4 to infinity. So you need to imagine what the original graph looked like to the point of memorizing it. Okay, just the original basic exponential function. And then from there you do transformation, then you see, oh, the range will be from -4 to infinity. Okay, now then how about the y-intercept? When it comes to y-intercept, then let's do computation. What happened to f0? F0 equals to 2 to the 0 plus 3 minus 4. That's 2 cubed minus 4, which is 8 minus 4. That's 4. So the y-intercept is 0, 4. Part D, how about the x-intercept? Because the range now includes 0 from -4 to infinity, right? So includes 0. So then there must be x-intercept where the y equals to 0. So 4 equals to 2 to the x plus 3. 2 squared equals to 2 to the x plus 3. That implies 2 equals to x plus 3. Yeah, the exponent equals to the exponent. Okay, and x equals to -1. So x-intercept is -1, 0. Horizontal asymptote, originally y equals to 0. The horizontal asymptote originally y equals to 0. Because I move it 4 units down, the horizontal asymptote becomes y equals to -4. Now, let's graph that in more detail instead of just the sketch. So the y-intercept is 0, 4, x-intercept -1, 0. Horizontal asymptote is y equals to -4, so that's the horizontal asymptote. Okay. But using only these two coordinates and horizontal asymptote, you won't be able to actually tell what the graph actually look like. Of course, you can say, oh, Thomas, can I plot more coordinates? Let's say x equals to 2, x equals to 3. Yeah, you can, but The way I see is grab the three important coordinates. Those three important coordinates were, remember, 2 to the x, right? That's the basic function, y equals to 2 to the x. That's 0, 1, 1, 2, and then negative 1, 1 half. Now, using these three important coordinates, move them according to the transformation. So let's say the 0, 1 here, the y-intercept, 3 units to the left, 4 units down. So it will land here later on. Okay. And then this guy 1, 2, move 3 units to the left, move 3 units to the left, and then 4 units down. It will land here. Okay. And then negative 1, 1 half, 3 to the left. So from here, 3 to the left, 4 units down, it will land here. Now I have a better picture that it will be like this, right? And then this one increasing. In fact, I get a lot of coordinates here. Okay, that's what it looks like. Now, after you're done with that, then you can use your eraser to erase what we had earlier. Okay, so those three important coordinates I told you earlier now move here. Okay, beside the x and the y-intercept, you use these three important coordinates to give you a better shape of what the graph look like. Okay, now when I ask you to graph this function, for example, the number of points for this graph is approximately 5 points. The number of points for this graph is approximately 5 points, one for each of these important coordinates, 1 point for the x, 1 or 2 points, 1 point for the graph of x-intercepts, and half point for y-intercept, half points for horizontal asymptote. Okay, so this is 5 points here. Now, why do I want you to do the graphing? When you take calculus for business later on, one of the weakness of a lot of students going to pre-calculus, going to calculus are they don't really know how to do computations, like these kind of things here. They don't really know how to do computations. Yet, even if they know how to do the computation, they don't know what it implies in the graph. And that's what I'm trying to prepare you with here. Okay. Now, again, it has something to do with how much you know also with the basic graph, plus how much you know about the transformation. So let's see another one. Let's call that example 2. What about, for example, I happen to see that here. How about let fx equals to 4 minus 2 to the x minus 3. Should I make it minus 3? I'll make it minus 2. Why not? Minus 2. So what will the domain be? The domain is easy. For exponential function, the domain is always all real numbers. The range question is the hard one, because you need to imagine what the graph look like and how it moves. So 2 to the x, let me use another color. This is my scratch word. So you do this on your scratch paper. 2 to the x looks like this. Now 2 to the x minus 2, move it 2 units to the right. Right? So you move 2 units to the right. Now, what happened with negative 2 to the x minus 2? Can anybody tell me what will this be? When you apply a negative in front of your function, you make it upside down. So the one that originally here now move here. Okay, that's what it looks like now. And then finally 4 minus 2 to the x minus 2, that's the same to negative 2 to the x minus 2 plus 4. Okay, that's what it means. So you can say you basically move 4 units to the right, 4 units up. The horizontal asymptote originally y equals to 0, right? Now you move up 4 units. Okay, so the graph may look like something like this. But from there we see that the range will be from negative infinity up to positive 4, not including positive 4. Oh, from there we also see that the horizontal asymptote is y equals to 4. Now the details. How about the y-intercept? Y-intercept of this function, f0 equals to 4 minus 2 to the negative 2. That's 4 minus 1 over 2 squared, which is 4 minus 1/4. Yeah, we can say this is 3/4, right? Or 3.75. Okay, that will be our y-intercept. How about our x-intercept? What our x-intercept? We set the y equals to 0 and then solve for x. 2 to the x minus 2 equals to 2 squared. So x minus 2 equals to 2, x equals to 4. Okay, so the x-intercept will be 4, 0. Now let's put things together. Graphing is essential in our learning because graphing enables us to see all things together. And that's one of the things you need to do. If you go to econ, if you go to business, you go to econ, then you don't see things partially. You don't see things partially. In my statistic class, we actually talk about the effect of lockdown. This is actually a bit off topics, but I'm trying to show you that when you start being, how to say that, I want to call that open-minded, instead of narrow-minded. The thing is this though, about this pandemic. If you want to tackle this pandemic, one thing you should do is actually lock down. Okay, but the problem is, how long is the lockdown supposed to be? Okay, because when you do lockdown, there must be a lot of people get impacted. A lot of people get impacted. One of them around my neighborhood. Actually, I live in an area where most of the industry is actually food. A lot of cafes, a lot of restaurants, hotels, tourism. Okay, so if you know where I live nearby East LA College. Like if you know Freeway 10 and then Atlantic, I live nearby that area. Now, if you go approximately 1 or 2 miles down, to the south, then you will get East LA College. Now, I live in this area. Okay. Now the thing is then what happened with the food, right? You cannot eat, you cannot dine in. You can only take out, but takeout already make people like then a lot of people who actually work part-time as waitress or waiters don't need to go to work anymore, right? Then the restaurant, the cafe don't need them. Okay, now you may say, Thomas, why you worry too much about those workers? Well, because a lot of those workers actually my students. They are my students. Okay, and because of that, then because it's now remote, then they don't need to actually live in this area anymore. Then they can go back to their hometown, right? Go back to East Coast or Central America, or go back to Asia, right? Okay, of course, that's what I would do if I were them. But what happened to those apartments that they supposed to rent now is vacant? That's that's from health point of view, you're supposed to lock down. But from business point of view, you cannot do it way too long. Now, from business point of view, that's really, really bad. Okay, and our businesses, we have seen in this 6 months or more, actually, this is 8 months already, half of the business in my area already down. I mean, they cannot recover anymore. And imagine the unemployment. Okay, now, of course, the government is supposed to help, but for how long? Right? Eventually, somebody need to pick up the tab, right? But if no business running, then the government will not generate enough tax. And if the government does not generate enough tax and still need to provide the stimulus, which I agree that they have to do it actually a lot earlier, but then eventually we will run out of money. You basically kick the can down the road for our next generation. Okay. So what happened is this, then there must be a balance between how much lockdown or social distancing we need and the effect on business. Okay, the business actually going to the food industry, hotel, apartments. Okay, and of course, because of that, then traveling also kicked down, right? And a lot of field. Now, the thing is, if you only see from the health point of view, then you say you're supposed to do lockdown, then you only see one side of the story, but you don't see what happened to other people, which eventually will affect you, right? Like, for example, do you enjoy this distance learning? Do you like that you don't need to drive to school? I say it in a nice way, right? But you know that math is not something you can learn. Math is not something you can learn well online by remote learning. No, it's not. That's not something. If you ask me, I prefer this though. I prefer this. Why? Because from me to move from one class to another class, all I need to do is actually log out, log in. I don't need to drive. I save a lot of money for driving. Right? So if I just want to think about me, myself, right, I will be safe from the social distancing. Because of social distancing, I don't need to see anybody. I'll be safe and I still make my money. Right? But how about you though? Do you learn well? The passing rate for this class and other classes, not only me, but the whole college, not only West LA College, but everywhere, the passing rate decreased by at least 1/2. Like what I'm saying is this: instructors who usually pass 80% of the students end up passing only 40% approximately. So you can say that he was a good teacher, but suddenly right now it's not. Imagine me that I usually just pass approximately 1/4 of my class. Now it's actually less than 1/4, a lot less than 1/4. Okay. Is it good for student? Hey, for me, I keep the same pay. But if I really think about my students, I don't want this to continue. It's not good for my students. And that's not my passion. That's not what I become a professor for. Okay. The reason I become a professor is not because I need the money. I need the money, to be honest. Right. But that's not the only thing I need. I have my passion. I want my students to learn well. Okay. That's why I don't discount my material. Okay. Now going back here, we will put things together into a better perspective. Horizontal asymptote. Okay. Y-intercept 0, 3.75. So almost 4, 1/4 less than 4. Right? And then x-intercept is 4,0. Now the thing is, this is definitely not enough for us to graph. So let's go back to these 3 important coordinates, 2 to the x. Right? Originally, that's what it looks like. Agree? Okay, that's what it looks like, right? Now then, use these 3 important coordinates, do the movement. What's the movement? 2 units to the right, upside down, and then up 4. 1, 2, 3, 4. So that y-intercept will later on land here. That's for the y-intercept. Okay, 2 to the right, upside down, and then up 4. Do it again, but this time to this 1, 2, 2 to the right, upside down, up 4. It will land here. It will land here. How about this guy? 2 to the right, upside down, up 4. 1, 2, 3, 4. It will land here. Now we have a better picture what it will look like. It will look like approximately like this. Now, if you ask me how I get these 3 important coordinates, that's from the original 2 to the x that I move according to the transformation. Okay. Now, that's also the reason when you take my test 4 later on, at least please print out some graphing paper. Okay. Otherwise, when you graph it, you need to put the coordinates. Okay. So please print out graphing papers, maybe 3 or 4 graphing papers. Such that when it comes to graph, you can graph it on that graphing papers and then you take the picture from there. Okay, so this is my scratch work earlier to see how it moves and help us to find the range and horizontal asymptotes. Okay, but we still need more than just transformation to put things into more fine, well-tuned, detailed graph. You need more than that. Okay. Now, some graph actually quite sneaky to graph. I don't expect to ever ask you this kind of question, but just to give you idea, what will you see, what you may see in calculus for business class. Let's say if I have 2, maybe this time I make it 3 to 2, yeah, still 2 to absolute x minus 3. How do you graph these, Thomas? How do you graph this? The domain is, of course, it's exponential function. So the domain is all real numbers. Whatever x you plug in, it will be well defined, right? But what is the graph of 2 to absolute x to start with? Now, 2 to the absolute of x is 2 to the x when x is positive or 0. That's 2 to the negative x when x is negative. It comes from this idea. It comes from that absolute of x is equals to x itself if it is positive or 0. But if x is negative, then you need to take the opposite to make it positive. Okay? Now, but because of that, this parallel to this. This parallel to this. Okay? Now then, we can now see these 2 to absolute of x as a piecewise defined function. You can see that as a piecewise defined function. 2 to the x, when it is positive, has this graph. That's what 2 to the x looks like. Okay? But that's for x is 0 or positive. Now, what happened to 2 to the negative x? Which, if you think about it, 2 to the negative x is 2 to the x reflected with respect to y-axis. That's 2 to the x reflected. You replace x by negative x. Reflected with respect to y-axis. Now you already have 2 to the x here, so you can just go on. That's the graph of 2 to the negative x. As if I'm saying this. This is 2 to the x graph. This is 2 to the x graph. This one. This one here is 2 to the x. But I only take the positive branch. And this is the graph of 2 to the negative x. But I only take the negative branch. So what happens if I want to graph 2 to the absolute of x minus 3? How do we do that? Let's see, what is the range first? From that graph, what is the range? Oh, that's the graph for 2 to the x, though, to the absolute of x. Now, this guy is actually 2 to the absolute of x times 2 to the negative 3. That is 2 to the absolute of x times 1 over 8. Okay, that's 1/8 of 2 to the absolute of x. So basically, whatever you have here, you need to divide by 8. Whatever you have here, you need to divide by 8. So 0, 1 becomes 0, 1/8. This is 1/4. This is 1/2. 8 divided by 8, that becomes 1. 1/2, 1/4. So it becomes like this later on. That's what it looks like. So the range is now from actually including 1/8 to infinity. Okay, because originally 2 to the absolute of x has the range from 1 to infinity. When you divide by 8, then the range becomes from 1/8 to infinity. the range of 2 to the absolute of x is including 1 to infinity. Now divide that range by 8. From here also we see that the y-intercept, that one is easy to see. When you plug in y equals to x equals to 0, the y-intercept is 0 and 8. We don't have x-intercepts, nor do we have horizontal asymptote. Okay? But again, this requires you to be able to analyze the situation. There's more than one way to graph this though. More than one way to graph this. But my preference is really you graph that 2 to the absolute of x first and then manipulate it. You can also imagine what happens if I have, for example, just continue from there. What about when I have gx equals to 2 to the absolute of x minus 3? Now this is the graph of 2 to the absolute of x move right 3 units. Okay, your suggested homework from here. Suggested homework 5.1. I would like you to do number 7 to number 15. Those are short questions. And then number 23, 25. What else? Number 31. Just graph it manually. And then number 51 to number 57. Okay, some word problems maybe it's possible to do. For example, number 69, number 71, and 73. No, not 71, just 73. 71 requires you to use graphing calculator. Let's say I do number 70. Number 70. Computer virus. The number V of computers infected by computer virus increases according to the model. Vt equals to 100 e to the 4.6052t, where t is the time in hours. V is the number of computers infected. Now you will see the following. This number 100 here is the initial value. We usually denote it by V0. If the notation here is V, then the notation here will be V0. What does it mean? At time zero, the initial number of computers infected is what? So you see, like what is V0? V0 equals to 100 e to the 4.6052 times 0. That's 100 times e to the 0. That's 100 times 1, which is 100. Okay, so the initial value, this 100 here, is always the same to the coefficient of any exponential function. Okay, now then the number here is the growth rate. You call that the growth rate. Okay, that's the growth rate. Now, for example, part A, the question is how many computers infected in 1 hour? Then you basically plug in t equals to 1. You can use your calculator for this. I hope you know how to use your calculator. Let me show you how to use your calculator. Give me a second. So how do we compute that? That would be 100 times. Now look for this E notation on your calculator. Okay, mine is actually here. E to the x, right? Second E to 4.6052 times 1. That's for my calculator, but your calculator may be different. So in 1 hour, we get more than 10,000 computers actually infected in just 1 hour. So 10,000.29814. Now, what happened in 1.5 hours? How many computers get infected? So going back to my calculator, that's 100 times e to the 4.6052 times 1.5. Okay, so that's 100 times e to the 4.6052 times 1.5. That will give me, that should be a big number. That's 100,004. 100,004.4722. So using this modeling, we see that within 1.5 hours, 100,000 computers get infected. Okay. The pandemic that we have actually follows what we call logistic modeling. Basically, it is like this. At the beginning, it is actually quite flat, and then it goes to what we call exponential phase. Now, once we have too many people get infected or immune from that, then it will slow down. And eventually, it will stay there. Now, this number means, that the number of people infected positive with that virus tends to be constant in long term. Okay, now what we are trying to do during this pandemic is try to make these horizontal asymptote here to be much lower, such that it is within the capacity of our hospital or of our healthcare system. Okay, so once we see that it is actually getting into exponential phase, we have to do that kind of lockdown. Okay, but of course, I'm just saying this from the math point of view. What is the effect of lockdown? You may have people get very depressed. I mean, I myself feel that because I stay at home for too long, trying not to get out, right? And I get much less sunlight, and therefore I get a bit kind of like mellow in more often getting mellow, especially reading those news about the election, this thing, that thing, you know. Okay, but yes, that's our 5.1. Let's go on to 5.2. 5.2 is the other way around. That is the logarithmic function. Logarithmic function and graph. First thing first. First thing first. What is logarithmic function? Definition. For a base, not the base positive and not 1, a to the x equals to y can be written as log base a of y equals x. Now, pay attention to the position. I hope this coloring helps. We usually say this is the exponential form. And this is logarithmic form. Okay, now we will spend a couple minutes just to learn how to rewrite them in logarithmic form. Now, suppose, for example, let's see number 8. Log base 7 of 343 equals to 3. That's the log form. What is the exponential form? Remember, this is the base. We call this the argument. The argument of log is the answer in exponential form, while the answer for log is the exponent. So in exponential form, this would be 7 to the power of 3 equals to 343. Base to the exponent equals to the argument. And yes, it does take a little time for you to kind of like remember this. Okay. Unfortunately, I think most of you do not experience the time when we still use that when we make a phone call and you need to remember the phone number, right? Like this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then right now we use cell phones, right? So very likely, I mean, we memorize very few people's phone number. Because what? You can just use your phone, look for the name, and then they associate the name with the phone numbers. But in the past, for example, when I need to call home, I need to remember the number, but I don't really remember the number, but I remember how I punch it. I remember that I punched this thing, and then here, 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 for example. So I need to remember the position. You see, I remember the position. Now, the way you do log to exponential form for exponential to log also follow the same pattern. Remember the position and how they move. So number 14, log base 8. Log base 8 of 4. The base here, base 8 here and base 7 above of the log is a subscript. It means it is a smaller and lower in size. The 4 is the regular size, equals to 2/3. So what will the exponential form be? That will be 8 to the power of 2/3 equals to 4. Okay, number 20. Suppose you have exponential form 4 to the -3 equals to 1/64. What will the log form be? Log base, the base is 4. The argument was the answer, 1/64. And if the argument is a fraction, use parentheses. This is equals to -3. Basic properties of log. Through these basic properties, it enables us to compute some, using the same technique we can use to compute some basic logs. For example, the first one, log base a of 1 is equals to 0. Why? So basically, I try to show you the proof. And hopefully from this proof, you see you can apply this to other type of computation. Why? Let log base a of 1 equals to x. Call that x first. Now we change this into exponential form. A to the x is equal to 1. But 1 is a to the 0. Right? By 1 to 1ness, x equals to 0. So log base a of 1 is equal to 0. Okay, basically, you ask yourself, a to what power equals to 1? A to what power equals to 1? So to answer log questions, when I ask you to compute log, sometimes one of the way to do it is by converting it into exponential form first. Now, for the same reason, you will see log base a of a is equals to 1. Now, why? Well, because we let log base a of a equals to x for now. Then you rewrite it into log 4 into exponential form, a to the x equals to that a. But a is a to the 1. Therefore, x equals to 1. Then log base a of a is equal to 1. The third, log base a of a to the x is equal to x. And for the same reason, actually, a to what power equals to a to the x? It must be a to the must be power of x, right? Okay, a to what power equals to a to the x? By 1 to 1ness, that what must be x. From here, we also see that logarithm actually cancels exponential. And finally, This is a result that we're supposed to see later. Log base a of x equals to log base a of y implies x equals to y. Okay. In other words, log function is one to one. Okay. But before I claim that log function is one to one, I will show you why it is one to one first. Okay, so our textbook say it is one to one without showing the reason it is one to one. Now, what is the reason? Here's the reason. And it's so important that let me call it a theorem. Let fx equals to a to the x for a positive and not equals to 1. So basically a regular exponential function. Then the inverse function of x is log base a of x. What I want to say that log function is the inverse of the exponential function. Log function is the inverse of exponential function. Okay. I will show you the work after this, the proof after this. But what I want to say is the following. We have learned earlier that exponential function is one to one. We know that. Okay. If we look back to our 5.1b, in the earlier part, I actually mentioned that fact. That because the function, exponential function, is strictly increasing or decreasing, then the function must be one to one. I hope you remember that. Okay, then the function must be one to one, right? Now, because the function is one to one, then we can find the inverse. The inverse is a function. Now we will show later on through that theorem that the inverse is a log function. Okay, but we also know that if the function is one to one, then the inverse of that function must be also one to one. Okay, and that's actually the final consequence we get for this part 4. Why log function is one to one? Because log is inverse function, and because it is inverse function, that log itself must be one to one. You start from one to one function to find the inverse, right? Now the inverse must be one to one also. Okay, now let's go back and answer that question. Show the proof that log function is inverse of exponential function. Okay, step 1, I basically do the inversing. Okay, step 1, y equals to a to the x. Step 2, I swap, x becomes y becomes x. Step 3, that's exponential form. Let me change it into logarithmic form. y equals to log base a of x. And step 4, f inverse x equals to log base a of x. Okay, now because f x I'm sorry, f inverse x, which is log base a of x, is the inverse of exponential function, then the big consequence, very big consequence, then we have this phenomenon. If you have fx here, which is a to the x, and gx here, which is the inverse log base a of x, then the following happen. The domain of exponential function is what? What is the domain of exponential function? The domain of exponential function, let's say 2 to the x, it's all real numbers, right? All real numbers. Now, then when you look at the inverse, that domain will become the range. The range of logarithmic function will be all real numbers. So you can answer the domain and range of logarithmic function by knowing the range and the domain of exponential function. The range of a to the x will be from 0 to infinity. Therefore, the domain of log function will be from 0 to infinity as well. Yeah, basically you can say that this x here, that x here has to be greater than 0. The argument has to be greater than 0. Okay, now some side notes then. Side notes. I did ask this in my pre-calculus class, and they just really mad with me. Some of them really mad with me. Some of them so really happy because what? I asked them this kind of question. For example, find the domain of log base 2 of 2x minus 3 over x plus 6, for example. How to find the domain? Well, all you need to solve is actually that the argument 2x minus 3 over x plus 6 has to be strictly positive. That's all, right? But then how to work further, then you start with that 3-step procedure. The critical numbers, right? And then the sign graph, and then the solution. Remember that? Okay, but that's the key step. This is the key step. The rest are things that we know what to do. Okay. Now, those people who usually rush to the solutions, especially depends on photomath, they don't know what to do. In fact, whoever used photomath in the first test, when they see this problem in their second test, none of them did it right. In your test 1, I trained you to do it by hand so that once your photomath cannot do it anymore, you still can do it by hand. Yeah, of course, then these students, I was talking about some students from Santa Monica. They were they cheat using photo math in the first test, but they didn't want to admit it. So fine, you know what? I will catch you eventually. You know, so their test 3, they say, oh, Thomas, I bombed this test. I say, you bombed your first test. You were cheating. That's why you feel that you're okay. And I'm someone who just tell you straight if I know that you were cheating. You don't admit it, that's your issue. But I will, we will find out later on. Okay, and yes, we did find out. Okay, why? Because the domain of log is that the argument, this argument here, has to be strictly positive. Okay, now let's go back. The y-intercept in the exponential function, which is 0, 1, that relates to the x-intercept in logarithmic function. That is 1, 0. Remember, the inversing happens when you swap. X becomes y, y becomes x. So y-intercept will later on becomes x-intercept 1, 0. That also explains that because x-intercept not exists in exponential function, basic exponential function, then in the logarithmic function, there will be no y-intercept either. Okay, horizontal asymptote that we have in exponential function y equals to 0, that will be x becomes y, y becomes x. So this will be x equals 0, right? But x equals 0 is not horizontal asymptote, that is a vertical asymptote. Okay, pictorially, suppose we graph 2 to the x. 2 to the x, we graphed that many times already. This is what 2 to the x looks like. When we do inversing, x becomes y, y becomes x. Basically, you reflect that function, the graph of that function with respect to this line. So the graph of the log function will be the one in blue. 2 to the x becomes log base 2 of x. Okay. The good thing is when the function, exponential function is increasing, the inverse is still increasing. Okay. And therefore, if it is the exponential function is decreasing, the inverse will also be decreasing. Okay, but we'll see that later. Now, in the last 5 minutes, let's do some graphing. Basic graph, at least just to make you memorize for the next 1 week. Okay, I have a plan. This Thursday, of course, we have no class. This Thursday, we have no class, but I plan to provide you one lecture video to watch during the weekend so that we don't become too far behind. We are actually 1 day behind because of this Thanksgiving. But let's see the graph for for example, for example, let fx equals to log base 2 of x plus 4 minus 3. Some students say that I use this function too often in my tests. So let me just go over it here. Part A, what's the domain? Look at the argument, x plus 4, right? Okay, so x plus 4 has to be positive. Remember, the argument of log has to be strictly positive. So the domain will be x greater than negative 4. So the domain is negative 4 to infinity. How about the range? Oh, the range for logarithmic form is already known. How do you know? Well, from here. From here. Yeah, so once the range is all real numbers, however you move it left, right, up, down, upside down, it will still all real numbers. How about the y-intercept? And f0 is equal to log base 2 of 4 minus 3. Now, what is log base 2 of 4? Log base 2 of 4 equals to what? Well, in exponential form, 2 to what equals to 4? Then that what must be 2, right? Because 4 is 2 squared. Okay, so log base 2 of 4 is 2 minus 3, that's negative 1. So the y-intercept is 0, negative 1. How about the x-intercept? You set the function equals to 0, log base 2 of 4 equals to 3. I'm sorry, not log base 2 of 4 equals to 3. Log base 2 of x plus 4. That's the original function. Minus 3. Move the 3 to the other side. And then change it into exponential form. From there we get x equals to 4. So the x-intercept is 4, 0. Okay, now how about the vertical asymptote? Now you will see that the vertical asymptotes always follow this. Basically, what makes this equals to 0? So the vertical asymptote is x equals to negative 4. Now what happened to the graph? Y-intercept 0, negative 1. X-intercept 4, 0. Vertical asymptote x equals to negative 4. And those three important coordinates were this guy, this guy, this guy. Where do you get those, Thomas? From here. This guy, this guy, this guy. Where do you get these three coordinates? From here. This guy, this guy, this guy. Remember these the three important coordinates in exponential? That gives you three important coordinates in logarithmic. Okay. Now then, from that three important coordinates in logarithmic, we move them according to the transformation that we need. The transformation we need is move 4 to the left and then 3 units down. So the new coordinate actually lands here. 4, or this guy. Okay, and then I will do the rest. This guy move 4 to your left and 3 units down, so it will land here. And this guy 4 to the left and 3 units down, it will land here. Okay, so the coordinates, the graph will be approximately like this. Okay. Now suggested homework from here. 5.2, number 7 to number 27, number 33 to number 49. Number 75, 77, and then 85 to 91. Just do the odd ones. Okay, that's for today.